Hey everyone, so today we're going to be talking about numerical summary measures. And this is going to be the first video on numerical summary measures. We'd like to have a sensible or a natural way to summarize data in a compact way. So if we had 100 data points, instead of looking at the entire data set, it'd be nice to have one or two numbers that could summarize that for us. And that's where summary statistics come in. Summary statistics give insight about useful features of distributions of data, such as measures of center and measures of spread. And we're going to be going over some very common measures of center and some very common measures of spread in a little while. All right, so a little bit on notation before we get going a little bit further here. First things first, n is going to represent the sample size. This is just the number of data points we have from our sample. And you'll find that n is just kind of like the universally accepted letter to represent sample size pretty much anywhere you go. X is going to be the sample itself, the data values. And we usually use this little subscript I to denote the ith observation from the sample X. So in other words, x1 is going to be the first observation, x2 is going to be the second observation, and xn is going to be the last observation from a sample x of size n. So let's clear things up a little bit with an example. Suppose we're interested in finding out the average age of all students at NIU. Now, instead of going and talking to each and every student and asking their age, it might be a little bit easier if we gather a sample of 20 students and use the average age of those students to estimate the average age of all students at NIU. So what do we have in this case? In this case, we have n equals 20. That's our sample size since we collected a sample of 20 students. And then the sample itself, x, is the collection of ages of all 20 people we talked to. And so x1 is going to be the age of the first student we talked to, x2 is going to be the age of the second student we talked to, and so on. All right, so the first measure of center we're going to be talking about is probably the most important measure of center in all of statistics, and it is the sample mean. And the sample mean, which is denoted by this symbol right here, it's known as x bar. It's a little x with a little bar on top of it. The sample mean is the average of n observations from a sample. Now, before I talk about the formula for a sample mean, think of what it actually means to calculate the average of something. So if I were to give you 5 numbers and say, calculate the average of these 5 numbers, what would you do? You would add up all 5 of those numbers and then you would divide by 5, right? Because you have 5 numbers. And that's essentially what we're saying here. All we're doing when we're calculating the sample mean, x bar, is we're summing up each of the observations from our sample, and we're then dividing by the total number of observations that we have, which is n. So this is just x1 plus x2 plus x3 all the way to xn, and then we're dividing that by n. All right, so let's look at an example. So suppose we ask 8 students how many miles they commute to campus each day. So in this case, n is going to be 8 because we asked 8 students. And the responses were the following. So the first student we talked to said they commute 32 miles to campus each day. The second student we talked to said they commute 14 miles to campus each day, and so on. So we're going to calculate the sample mean here. So to calculate x bar, remember, all we need to do is sum up each of the values from the sample and then divide by the total number of values that we had. So in this case, we're summing up all of these guys together, and then we're dividing by 8 because our sample size was 8. So when we do that, we get 106 divided by 8, which comes out to be 13.25. So on average, the 8 students we asked commute 13.25 miles to campus each day. All right, so the next measure of center that we're going to talk about is also super common. It's called the sample median. And the sample median is denoted by this symbol right here, and it's known as x tilde. And the sample median is nothing more than just the middle number when the data values are sorted from smallest to largest. All we need to do, if n is odd, x tilde is going to be the middle number. It's going to be really nice and easy. If n is even, it gets a little bit tricky because then there are going to be two numbers in the middle of the data set. So in that case, x tilde is going to be the average of those two middle numbers. So let's look at a couple examples here. So we're going to look at an example when n is odd. This is the easy case. So suppose we have a data set with these values right here. And so the first thing we need to do when we're looking for the median is we need to sort the values from smallest to largest. And when we do that, we end up with this. And what we're looking for the median is the middle number. And in this case, 3 is that middle number. So the median of this data set is 3. So what happens when n is even? When n's even, it makes things a little bit more difficult because there isn't just one middle number that we can pluck out of there. So suppose we have the data set that looks like this, and just like before, when we're looking for the median, the very first thing we have to do is we have to make sure the data set is sorted from smallest to largest. And when we take this up here and sort it, we end up with this. And you'll notice now that the middle of this data set is in between this 5 and 6. So what we have to do is we have to take the average of 5 and 6. And we already know how to take the average. It's just the mean of those two numbers. So we add them both up and then we divide by 2 because there are two of them. And we end up with 5.5. So in this case, the sample median is 5.5. So we may want to describe the shape of a distribution of data as well. And one very common way of doing that is called the skewness. And the skewness refers to the lack of symmetry in the distribution. So if the tail of the distribution is toward the left, we say it's left skewed or negatively skewed. Conversely, if the tail of the distribution is toward the right, we say it's right skewed or positively skewed. And if it appears that there's no skew at all, or a very small amount of skew, and the distribution looks to be roughly the same on both sides, then we say it's a symmetric distribution. And here's what that all looks like. So on top here, we have an example of a symmetric distribution. Now, this is definitely not the only symmetric distribution out there, but this is an example of one. Because if we were to draw a line down the middle here, it would look roughly like a mirror image on both sides. And down here, we have a left skewed distribution. Now, be careful here. It's very easy to get left skewed and right skewed mixed up. I remember when I was first learning about this concept that I would confuse them all the time. So be careful. The easy way to remember this is to just look at where the tail is going. So this is left skewed right here, and the tail is off to the left here. So since this tail is off to the left, we could say this is negatively skewed or left skewed. And just like over here, the tail is off to the right, so we would be able to say, oh, this is right skewed or it's positively skewed. So that's kind of what those look like. But one of the nice things about skewness when it comes to mean and median is that we can know if a distribution is skewed one way or the other without even having to look at it. So if the sample mean is less than the sample median, then the distribution is going to be left skewed. Conversely, if the sample mean is greater than the sample median, then the distribution is going to be right skewed. And if they're roughly the same, if the sample mean is approximately equal to the sample median, then the distribution is going to be approximately symmetric. And we know this because the sample mean is more sensitive to outliers than the sample median. And it's also equivalent to say that the sample median is more resistant to outliers than the sample mean is. And if you're wondering what outliers are just values that are far away from most of the other values. And there's a formal definition of outliers, but for right now, we can think of outliers as data points that are really far away from everything else. So let's look at an example. So suppose there are 8 people in a room and we know what their annual incomes are. So here are the 8 salaries of the people in the room. And if we were to calculate the mean and the median of these incomes, we would end up with a mean of $44,000 and a median of $41,500. But now, suppose a surgeon who makes $404,000 walks into the room. Now, this is an example of an outlier. We have all these salaries and we have a general feel of where these salaries are. And then someone who makes way more money than anyone else walks into the room. This is an example of an outlier. So now we update these incomes, and these are all the incomes we had before, and we've added the $404,000 income from the surgeon on here. So if we were to recalculate the mean and the median of this updated data set, we would have a mean of $84,000 and a median of $42,000. So look at what happened to the mean and the median here. This mean went from $44,000 to $84,000. It increased a lot. Whereas the median was 41,500 and it just went up to 42,000. So the median barely moved at all. So like we say down here, the addition of the outlier caused the mean to increase much more than the median. This is what we mean when we say the mean is more sensitive to outliers than the median is. And when we add this outlier in here, the mean is much higher than the median. And just like we learned before, since the mean is much higher than the median, we know the distribution is right skewed. So another common way to describe the shape of a distribution is called the modality. And the modality refers to the number of modes, hence modality. And the modes are just the peaks or the humps in the distribution. You can think of them that way. So if a distribution has one peak, then we say it's unimodal. And if a distribution has 2 peaks, then it's said to be bimodal. So notice these prefixes here. Uni means 1, bi means 2. So 1 peak means unimodal, 2 peaks means bimodal. And if a distribution has more than 2 peaks or humps, it's said to be multimodal. So let's take a look at what these look like. So up here, we have an example of a unimodal distribution. And we know this is unimodal because it has one peak, this one peak right here. And this is definitely not the only example of a unimodal distribution, but this is an example here because it has one peak to it. Just like down here, this is bimodal because it has 2 peaks to it. So these 2 peaks make it a bimodal distribution. And then finally over here, we have a multimodal distribution because it has more than 2 of these peaks, more than 2 of these humps. So that's all for the first presentation on numerical summary measures. I hope you found this video helpful, and I will see you in the next video.